Well, I'd like to welcome you to this Top 500 BOF. We have a pretty full session today, and this Top 500 list is special in a number of ways. This is our 30 years, 60-second list. So 62 times we've collected data on the Top 500 list. We have a full session. You can't see it, but you will in a second. There we go. So we have a full session today. We're going to start by giving out the awards, and I'll be accompanied by Eric Strohmeyer, and Wu Fang will join us in some of these awards. We'll follow on with the student cluster competition and describe the winner of the HPL runs. And then we'll have a short talk from Rick Stevens on the Aurora system, followed by Prabhat talking about the Eagle system. Eagle system is a system that came to us through Microsoft, and it's also one of the new entries. Jack Wells will give a little ad for a BOF that's being run tomorrow on the future of benchmarking, and then Eric will go into his list of the Top 500. So let's begin, I guess, with the awards. So we're going to go through this hopefully quickly, and we're going to sort of bunch the awards together. So the first award is for Frontier, who scored #1 on the Top 500 list with a score of 1.194 exaflops. And I guess I would like to ask the people from Oak Ridge and also HPE to join us on stage. So Al Geist, Gina Tarasi, and who's the other person? Only them. Okay. Oh, here it is. That's right. So this is for the Top 500 #1. Pictures here. I'm going to look at the real camera person over there. This is the fake guy over here. Okay. Oops, so one more. Okay. And don't go away. In addition to being #1 on the Top 500, they also scored high on the other benchmarks. So the HPCG, they are number 2. On the HPL Mixed Precision benchmark, they were #1 with an amazing score of 9.94 exaflops. And they have a certificate for the Green 500 as well. So congratulations on the machine. Quite an impressive device for doing high performance computing. Congratulations. The #2 award for the Top 500 goes to the Aurora system. It achieved a performance of, now I can't see it on this slide here, so we don't have the actual, oh, we do have it there, 585 petaflops. So maybe I can ask Rick Stevens to come up, and also the Intel guy whose name I forgot. So that's. Looking at the lady there with the white shirt. Yes. All right. Now we can look at the other cameras. Thank you. All right, thanks very much. The #3 award on the Top 500 goes to this cluster system that's put together on the cloud called Eagle. It's from Microsoft. It achieved 551 petaflops, very close to the #2 system. Maybe we can ask the Prabhat and who else is coming up from? Oh, they're all coming up. Yes. Prabhat, Jinta, and Jack. Is that right? Yes. Hi. Thank you so much. Jack. Anything else with John? Sorry.
Thank you so much.
And then we have to squeeze over here. Move over this way. This way. Move it more. So that's the camera guy.
All right. Thank you so much.
Congratulations. Our next award goes to the #1 system in Asia. That's the Fugaku system. It ranked #4 on the top 500 list, and to accept the award is Satoshi Matsuoka from Riken. You have so many awards here, Satoshi. we lost the screen. So we're looking over there now. So the Fugaku system was #1 in Asia, #4 on the top 500. It scored #1 on the HPCG benchmark, and also it scored #3 on the HPL mixed precision. Thank you so much, Satoshi. Our next award goes to Lumi, which is a Cray system. It ranked #1 in Europe, so maybe we can have our Finnish friends and European colleagues come up. So let's see, this is Justin, Andres, Pekin, and Kimo. She's the boss. Now we can go to #2. #2. We got multiple cameras. That's right. Fault tolerant here, redundant computing.
Do you have film enough?
Yeah.
Needs to be widescreen.
Widescreen, very wide. It's taking a movie. Okay, thank you. Thank you, guys. Oh, we didn't quite get that finished up. So just hang on, guys. Just hang on. So not only were you #1 in Europe, you were #3 on the HPCG benchmark, and #2 on the HPL mixed precision. Well done. And next, we're going to turn it over to Wu Feng, who's going to give us some of the Green 500 results. So you just have to press that button.
All right, for the Green 500, #1 machine, again, is Henry at the Flatiron Institute in New York. It's a Lenovo ThinkSystem SR670 supercomputer. It achieved 65.4 gigaflops per watt. You have the folks, representatives. Wait. Let's see. We're going to jump to number 3. Number 2 was already presented. Actually, it was to Frontier TDS, which has been, I believe, renamed Crusher. So that was for the number 2 system on the Green 500. The number 3 system is Adastra. It's an HPE Cray EX235A system. We have representatives from Adastra to come up.
It's a very complicated position here. Okay, so just a little bit more about the Green 500. There's a BOF tomorrow evening. I think it's at 5:15 that we will really go into more detail about the Green 500 and the implications there. So, so please join him for that. We'd like to give a shout out to the student cluster competition. This is something that's held every year here in multiple places. And this is a team partnership with vendors helping to design and build HPC systems that are configured, and they run benchmarks on them. They run a series of real-world scientific applications. There's a 2-day competition that takes place. If you go down to the exhibit floor, they're in the back of the room there, and it's quite impressive to see what they're doing and how they're doing it. So the core benchmarks are the HPL benchmark, HPCG, MLPerf. They also have streams and the OSU latency bandwidth benchmarks. And during the benchmarking, the teams are constrained to a power budget of, this year it's 4 kilowatts power limit, and they must use at least 2 nodes for the HPL and the HPCG run in order to make it fair for everybody. So out of the 4 out of the 11 teams achieved an HPL score above 100 teraflops, and the winning run was made on an 8 NVIDIA H100 GPU with 24-core AMD system, consumed 3.8 kilowatts and achieved 181 teraflops, and that was done by Peking University's supercomputing team. So maybe I can ask them to stand up and take a round of applause. Good jobs, guys. Very impressive. I'm going to move on, and Rick Stevens at Argonne has a very interesting machine that just is coming online, and he's going to tell us a little bit about that system. So take it away, Rick.
Thanks, Jack. So this was a picture taken in June when we put the last blade into Aurora. There's Susan and the team from Intel and HPE, so congratulations for them. I'm just going to give you a little bit of info about the machine. So it's a big system. It's 166 of these large Olympus-sized racks. It's 10,624 nodes. You get that by 166 times 64 nodes per rack. We have 2 of the Sapphire Rapids with HBM CPUs per node, and 6 of the, I guess, Intel calls them GPU Max, I guess now. It's a hard name for me to remember, but these are PVCs. There's 6 of those on a node. And it's HPE Slingshot 11 interconnect with a very large network. There's 8 network ports into every node. And we also have, so the system, if you look at the peak numbers, is over 2 exaflops. Almost all that's coming from the GPUs, of course. And then in memory, there's a lot of memory. So each of the PVC GPUs has 128 gigabytes of HBM2E. And then because we have Sapphire Rapids with HBM, there's another 1.3 petabytes of HBM that's actually sitting on the CPUs, and then about 8 petabytes of, or I guess I read it wrong, 10, almost 11 petabytes of DDR5 in the machine. But anyway, a lot of memory, and an amazing network, and maybe something that most people don't know about is we're standing up a large Deos infrastructure that has an enormous amount of bandwidth, about 30 terabytes per second of I/O bandwidth. There's some pictures. The status right now is we're about halfway through what we'd call the stabilization and commissioning process. And of course, we put a LIMPAC submission in, but that was on a subset of the machine. Starting in the next few weeks, we'll be getting more early science and ECP project access on, kind of in parallel while we continue stabilizing the machine. I thought I'd show a little bit. Here's a picture. You have a node, in case and there's a nice movie from Intel down there, but it gives you some of the specs here. There's a back-end network that connects GPUs to each other. There's 2 PCIe Gen 5 switches. This doesn't show the HBM on the Xeons, but it's there. And then the 8 Slingshot NICs that are on the node. So a node's over 130 teraflops peak. So this is the Sapphire Rapids, which also has, well, I mentioned HBM, PVC. This is an amazing device. I think this is probably, on the show floor, probably the device with the largest number of chiplets, with over, 47 tiles, right, on 5 different process nodes. And over 100 billion transistors, so it's an amazing device. Just to give you a sense of the kind of performance we're seeing on real applications, and we're comparing this to an A100, not because we don't love NVIDIA, we do love NVIDIA as well, but just because everybody kind of knows what an A100 kind of can do, and what we're seeing here, this is real apps that a few of them are less than one A100, but a lot are above that, and some are more than 2x an A100. So one way to think about our kind of expectations on the machine is that we're somewhere between an A100 and an H100 in terms of performance. And some of these are on 2 tiles. A PVC has 2 tiles, so some of the light bars here are actually 1 tile runs that we scaled up, but we get almost perfect scaling for many of these applications. So that's the update, and thanks.
And next is Prabhat, who will tell us a little bit about the entry that was put forward by Microsoft and scored number 3 on the top 500.
All right, thank you, Jack. I represent the Azure HPC team. There are a bunch of our colleagues sitting in the back there. So this is for the number 3 entry, but I first do want to acknowledge and compliment my ex-DOE colleagues and the Oak Ridge team sticking with the number 1 slot. I think it's been really promising to see that system become more productive for scientists, which is really the eventual goal. And it's a collective sigh of relief for all of us to see Aurora come online. And congrats to Rick, the Argonne team, Intel, and a number of people who've had an important role in bringing the system online. I think the IC rankings are going to be interesting in 6 months to see where things land up. But today I'm going to be representing the Microsoft team, chatting about Eagle, which is our new entry. So we obtained 561 petaflops, which landed us the number 3 slot. This is a vanilla NDV5 H100 supercomputer. We've had a lot of questions, I think, in the last 24 hours around, is this custom built? Is this a one-off? Was this built for HPL? So on and so forth. No, no, no. This is a vanilla supercomputer that any Azure customer can use for running HPC or AI workloads. It features, this particular submission was run on 1,800 servers and has 14,400 Hopper GPUs, H100 GPUs. And this is, it leverages the InfiniBand NDR, 400 gigabit per second technology. So this is probably NVIDIA's highest ranked, in terms of systems that are using NVIDIA GPUs and InfiniBand. This is the largest system on the top 500 this year. So again, this is a commodity VM that you can use. We've always claimed that this can be scaled to thousands of GPUs. Well, you have the proof in front of you now. It has been engineered specifically for generative AI applications. It's no secret that Microsoft is investing tremendously in AI. So this was designed for our flagship AI customers, and certainly is capable of enabling a new generation of large-scale models, which are being used both internally and externally. So this is how you build a supercomputer. I guess you start with a bunch of GPUs. In this case, it's a Hopper GPU, has 80 gigs of HBM memory. We have PCIe Gen 5 on our servers, and on our servers, we have 8 GPUs. So this is a pretty dense form factor. Then we're using NVLink to connect all of these 8 GPUs. We get 3.6 terabytes per second bisection bandwidth, and we are able to get close to 150 gigabytes per second all-reduce performance. All-reduce happens to be a communication pattern that's important for AI workloads. And then finally, you chain together all of these servers using InfiniBand. So factory topologies are the topologies that we use. We've experimented with non-blocking factories. This is tapered a little bit. And we've certainly scaled this out again to thousands of GPUs. 400 gigabits NIC cards, so there's a one-to-one mapping between GPUs and NICs. And then on a server basis, you can get 3.2 terabits per second. We certainly use GPU direct RDMA. Now, from a programmability perspective, as long as you're using the latest and greatest nickel, it is fully aware of NVLink, NV switches, it's aware of IB, it's aware of the topology. So really, from a programmability perspective, it's really quite easy for users to just write up a PyTorch code and scale it up. And we also had a fairly easy time in scaling up HPL. All right, so this has been a journey. Again, for some of you, this may come as a surprise, but again, Microsoft has been investing heavily in both AI and HPC. So of course, this is the number 3 ranking for us, but this is the top submission for a cloud provider. Every year to year for the top 500 rankings, we've had 19x performance increase, and then list to list, it's about 10x. So again, it's a fairly deliberate, systemic strategy to make a mark, I guess, in this field. So that's all hardware infra. I really do want to comment on the software bit, because that's sometimes ignored in the cloud business. So again, nothing special here. We have a classic Ubuntu-based image. So Jitin Jose, who's sitting right there, he curates that image, and he makes sure that it's tuned and runs well in an out-of-the-box sense for customers. So you can today download this image and use it on this particular VM. It will work. We work very closely with NVIDIA to tune Nickel and HPCX, and that's, again, included in this particular image. And then finally, I do want to pause and acknowledge NVIDIA's contributions here in that their HPL container was pivotal for this submission. I think we had days, not weeks, to pull this off. And I was suggesting to the team that we start conservative, run on 10 GPUs, 100 GPUs, 1,000 GPUs, 10,000 GPUs. And basically, this container worked seamlessly well. So I think it was a fairly easy task for us to scale this out to the entire machine. So again, kudos to NVIDIA, and we really appreciate their collaboration. All right, so again, put all of that together, you throw a real benchmark at it, and this is what you get. So on a per GPU basis for Hopper, the theoretical peak is 57 teraflops, FP64. We were able to obtain 45.5. That's about 80% of theoretical peak. And of course, when we scaled it out to 1,800 servers, the scaling efficiency that we got at the 1,800 VM or server level was about 86%. So that's acceptable for an HPC workload at scale. If you just look at the raw flops, the performance that we got was about 66% of theoretical peak versus the theoretical number of flops that would be on a Hopper GPU. So not too bad. I did mention early on that this machine was designed for AI workloads. That's where our flagship customers are. So I do want to mention that at this point in time, beyond the mixed precision benchmark that's in the top 500 suite, MLPerf has, I think has helped rally the community around systematically putting out benchmarks, scaling them out, so on and so forth. So last year, they put out this LLM, a large language model, 175 billion parameter model benchmark. And the earlier record was for this particular benchmark, run out to solution taking about 10.9 minutes on 3,500 GPUs. So this year, on this particular system, we smashed that record. We essentially were able to converge this particular model in 4 minutes using 10,000 GPUs. So for that particular benchmark, we were the #2 submission. If you look closely, it's a near statistical tie between NVIDIA and CoreWeave submission, but we are definitely the #1 cloud provider. So I think the writing is on the wall. Azure has made a lot of investments in AI and HPC, and capability class computing for both AI and HPC workloads is in the cloud, is on Azure, and available to all of you. So thanks very much. These are the email addresses for people if you want to reach out to us. Jack, John Lee, Jitin are there in the audience. Catch up after the BOF, and you can find us on the booth as well. Thank you.
And next on the list is Jack Wells, Jack Wells from NVIDIA, who will tell us a little bit about his BOF tomorrow. You have slides?
Yeah.
Of course you do, yes. So let's unplug this one and put this one in. And maybe that'll work. Let me just close this and you can put it right on top.
Okay, it's okay. I'll just talk. Yep. So thanks for the opportunity to participate in this BOF by advertising our BOF tomorrow night on the future of benchmarking and supercomputing.
Let's try one more time. You got too many dongles.
So this BOF that's scheduled for a 5:15 time slot tomorrow is organized by Rangan Sukumar and Artie Garg and myself on, again, the future of benchmarking and supercomputing. It's motivated by the expansion of use cases, the new AI applications like we've just seen in the previous talk from Prabhat, other concerns about energy efficiency and benchmarking, energy to solution, and just how we should be moving forward in the future. So we want to talk about things like why we do benchmarking, for example, to track progress in science. It's all right, I'm not, it's okay, it's okay. Why we do benchmarking, what we hope to achieve from benchmarking, and how we hope to improve the quality of our communications and marketing around benchmarking. We want to encourage open collaboration on HPC benchmarks, think beyond LINPACK for scientific benchmarks, and hopefully inform workshops that will occur in 2024 if the community has a lot of enthusiasm for this topic. And I'll just say some of the panelists that we've lined up are people like Piotr Lustig from the University of Tennessee, Dan Ernst from NVIDIA, Jens Domke from Riken, Shantanu Jha from Brookhaven and Rutgers, and Steve Farrell representing MLPerf, and Ritika Borkar representing ML Commons. So if you'd like to participate in the conversation, 5:15 tomorrow in room 702. Thanks so much.
Thank you, Jack. I think it's an important thing to have input from the community in terms of these kind of activities, and also to expand the range of benchmarks that we consider. Some of the benchmarks we have are pretty long in the tooth, and having the ability to put new things into the mix, I think, is a good idea. So let's see, we're going to now turn to Eric Strohmeyer, who will tell us about the top 500, as soon as I can find the right place here. That's interesting. So there was supposed to be another set of slides here, but maybe they got lost in the mix. We'll get it. Let's do this. So I think you want this one here. Floor is yours.
Thank you, Jack. Good evening, everybody. Thanks for sticking with us. It's my pleasure to give you some of the highlights of the 60-second top 500 list. The first time we were at SC was in '93, and we have done it every year. So I'm quite proud of that. Here we go. As usually, I'm going to give you the highlights of the various top 10s according to the different matrices, benchmarks we measure and we track, and according to the power efficiency, in terms of the Green 500. I talked in the past already about the changing structure of the list, and I'm going to highlight that briefly again, and how that relates to the changes we see in the market and the underlying technologies we use, and what that means for the list and what we actually predict for the future of the market itself. And as the list is becoming a little less dynamic, as I'm going to point out, I'm going to focus for my usual statistics. I'm going to focus on what happened last year. So I'm going to focus on the 91 systems which are new, which have been installed since SC23. So with that, that's the new top 10, which has been published yesterday mid-afternoon. And as usual, in yellow, you see all the changes to the top 10 compared to June. You see there are 4 new systems on the top 10. That's an unusual high number these days. Most lists, we only have 1 or 2 new systems. So that's a fairly high turnover. It's nice to see. And of course, at position number 1 is still the Frontier system, has been for a while. It's the only system which has been measured on HPL with over an exaflop. So in that sense, it's the only exaflop system we are aware of. The new system at position number 2, the Aurora system, or Argon, of course, is supposed to be, in the end, is going to be larger than Frontier. It's going to be a 2 exaflop system. And Aurora, they submitted an early measurement to us, which was run on half of the system, which achieved an HPL score of over 580 petaflops, which was high enough to be number 2 position, and we expect that system to show up even higher in the future. The number 3 system might have been a little bit more of a surprise, the Eagle system, and you heard Prabhat talk about it. It is the highest ever ranked system, commercial system, and the highest ever ranked cloud system. It exemplifies a couple of things to me. We have talked about how in the research market, research installation, there has been a large concentration of computing power at the top, and we now see actually the same happening in the commercial market. It probably has happened just in parallel to the research market all along, but now with systems like Eagle, we see that there, even in the commercial market, there is a concentration to fewer, larger systems at the very top, and that's one of the that's the first really dominant example we see in the list for that. Aurora, as Rick earlier mentioned, of course, is also very interesting because it is one of the systems which uses new technology, new chip generation, in particular the Intel Sapphire technology, and they're using it for the CPU as well as the GPU. It's not the only system in the list. There are actually now four systems came into the list using Sapphire GPUs, and we have a total of about 24 systems using Sapphire CPUs now in the list. That's probably within the last year the biggest new generation of chip technologies, chips coming into the list. At position number 5 is the Lumi system, which has achieved a couple of awards here. You saw that earlier. They have been on the list a couple of times, but they have I touched something, which I didn't mean to. Here we go. So the Lumi system was upgraded a couple of times. That's part of their installation policy. So every time their system is a little larger than it used to be. They achieved now a benchmark of 380, which didn't really change their positioning because they were moved down by the newcomers at number 2 and number 3. It's still the largest system in Europe. It's one of 2 Euro HPC systems in the top 10. The other one is the new system at position number 8, installed in Barcelona. Sister installation, but through the same funding stream as funding agency organization, Euro HPC. So that's a Mare Nostrum system. It is notable there is, for instance, that it's a European integrator and manufacturer, Eviden, which is actually very successful, especially in Europe. So it's nice to see that there is a variety going on. And the number 9 system, the 4th new system in the list in the top 10, is also notable because it's another commercial installation. It's actually an NVIDIA system installed at NVIDIA in-house. And it's another example for the accumulation of more large systems at the top in the commercial space, not just in the research space. So overall, we were quite happy to see such a high turnover in the top 10. So I looked, was there actually more turnover in the top 500 than usual? If you just look at the whole list, it was actually very average. But if you look at the top 50, it actually changed quite a bit. That's why, for a change, I put down here the next 10 new systems which came into the list last year. So this is past position 10. You see on the left-hand side the current positions. The spread of the new systems is between position 15 and 52. That is much, much more than we have seen recently. Just as an example, only the first one of these 10 systems, the one on position number 15, entered the list in June. There was only one new system in the top 50. All the 9 others came in the November list. And one of the reasons that I wanted to show this is because this list here is really very diverse. If you look at it, it starts with where these systems are installed. It's 9 different countries. You have countries like Saudi Arabia, South Korea, and others. You have a lot of the European countries. So there is no clear dominance. It's very broad. It's very diverse. We have 7 different manufacturers. And it starts actually with Microsoft Azure again. That's the second biggest instantiation of that system in the list. And then, for instance, there is a company I wasn't aware of before this list, Nebius AI. That is basically a cloud AI provider startup company in Europe, which put up a big system, and it's big enough to be in the top 20, position number 16. So there is a lot of change going on in the industry and in the commercial space just as much as in the research space. Two more things I want to point out. The position 8 and 10, third last and last system, those are 2 other examples of systems with Intel Sapphire GPUs. That's the Intel Data Center GPU Max is the official name for that. So they have similar architectures, they have similar chips at least compared to Aurora. So those systems are coming in fairly high. Those are 2 research installations, obviously, but from different integrators, from Dell and from Lenovo. So it's not just Intel which uses their own chips, but it's actually other companies too. And in between at position 50, which is the second to last one, there is the NEC SX Aurora system, which I always like because it's a system, it's a traditional vector system, and it's really optimized towards data access in a way we can't afford for a lot of other systems anymore. And it's notable because even so it's only position number 50 in the top 500, because of its high memory access speeds, it does actually very well on the HPC-G benchmark. And with that, I'm actually going back over to the top 10s, and I'm going to show you the top 10 of the HPC-G benchmark. And if you look there, you see at position number 10 in the HPC-G benchmark, there is that NEC SX Aurora system, which is on position 50. So it's much more well suited for something like an HPC-G benchmark than an HPL benchmark, even though it's doing very well on the HPL benchmark as well. The other thing you might notice is there is much less yellow on that slide. That is actually true. And there's a mixture of reasons. One is that commercial systems like Eagle or NVIDIA, they tend to only submit HPL, if anything at all, and not HPC-G. Maybe they're going to do in the future and show up here as well, but you're not going to find the commercial systems in the HPC-G because it's a secondary priority to them. And early systems like Aurora, they might also submit HPC-G numbers after they get the whole system shaken out and so on and so forth. So you're not going to find Aurora on this too. So none of the 4 new systems in the top 10 actually gave us an HPC-G number. That's why the HPC-G list is basically the one from June, except for that vector system in Japan. On the very left, you see in green, I noticed reorderings, and there is certainly a lot of these systems ranked much higher in HPC-G than in HPL. Part of that is missing HPL numbers. Part of that is that these systems have architectures which are much better suited to HPC-G, which you can see on the right-hand columns where you see efficiencies. So we started tracking a different benchmark altogether, also developed by Jack. So all these benchmarks so far have been developed by Jack. and that is the HPL mixed precision benchmark, HPL MXP. And that data collection is still much smaller. We have much fewer systems. Piotr Luszczyk is compiling those numbers, and this is the top 5 in the HPL MXP numbers. So what you see there, we gave out the awards for Frontier, Lumi, and Fugaku. That's the systems which have been there, the first 3 positions before, followed by Leonardo and Summit. The reason that we point this out is with the mixed precision benchmark is that this is really a showcase for what you can achieve if you innovate in software. So the 2 columns I highlighted through bold numbers give you a fictitious floating point number in the middle, a floating point number. A system running only 64-bit code would need to achieve to get the same time to solution as these systems have. So to match Frontier's time to solution on that mixed precision benchmark, you would have to have a 10 exaflop system running 64-bit code. And that is quite a bit of a speed up, and the speed up is the rightmost column, and you see we see speed ups are close to up to 10. So if you invest in the software, in the mathematics and software, to really enable and use efficiently something like mixed precision, you can get a factor of 10 speed up, which in the old days wasn't that much. You waited 2 or 3 years and you got that from the hardware. But nowadays, as I'm going to show, you're going to wait 10 years and there is no guarantee that you have 10x at all, even in 10 years. So 10x is quite a bit of a speed up. There's quite a bit of payoff. That's why these technologies are becoming more and more, software technologies are becoming more and more interesting. So HPL MXP, and with that to the last top 10 list, which is the Green 500. So Green 500, there we rank systems by how much performance, how many floats we get per watt used, and we use the HPL benchmark as a workload. That is a technology ranking and not a ranking by size. That's why the content of the top 10 on the Green 500 usually looks very different from the top 500, and you shouldn't expect that a top 10 system shows up in the top 10 of the Green 500. However, for instance, the Mare Nostrum system, which is here now number 6, there is a top number, is the number 8 in the top 500. So that is a very big system. Having a big system doesn't prevent you from being power efficient. You can still do that. You have to have the right architecture and the right software, obviously. Usually, because this is a technology-based list, there is a lot more turnover in the Green 500 than in the top 500. This is one of the first lists where it's clearly the other way around. We have a lot more new systems in the top 500 than in the Green 500. Part of that is that some of these systems have not given us power numbers, so we don't know where they really are. But part of that is just there wasn't as many new technologies coming in the last year. Having said that, we see a continuous growth, a continuous improvement in power efficiency across all levels of performance in the top 500 through tracking in the Green 500. But we also see a steady increase in power consumption across all levels in the top 500. So the increasing power consumption has not stopped and continues to go. And we have to see where this actually goes, where we end up. There is the in-depth BOF session tomorrow, which I advertise. And unfortunately, like it is with BOF sessions these days, it runs parallel to one from Jack Welch about benchmarking. So you're going to have to decide tomorrow. And Jack actually, he had to leave because he's running another BOF session right parallel to this one. So he had to sneak out and come here. But I guess that's SC. So what happened in the list, I already said that. But the list overall, other than the top 50, had actually a very low turnover rate. Only 45 systems fell off the edge because they were too small. That's very low. And this low turnover rate, which has developed over the last decade, that goes hand in hand with us actually running our systems longer and longer. And that reflects itself in the list by the systems in the list being older and older, not just in the list, but actually in the field. The oldest systems on the list now are 12, 13 years old. There are only a few, but they are there. And 10 years ago, a decade ago, if we had a 10-year-old system, we sent a little email to the site and said, do you really still run that? And the usual answer was, no, it was an oversight. We forgot to remove it. It doesn't work. It's not in operation for the last couple of years. If we do that these years, if we do that now, Typically, the answer is yes, we're still running that system. So those systems are really that old. And there is no end in sight. Our systems are getting older and older because there is less and less incentive from the hardware point of view to replace them, and we rather save the money for one more year and then spend it to buy a larger system. Okay? So the other effect we have seen over the last couple of years was this concentration towards the top, that the list is becoming more and more top-heavy. And to look at that, we look how dynamic is the list in terms of performance. So this time with Aurora and Eagle, about 30% of the performance in the list is new. But that is driven very much by those big systems, in particular by those two systems. Because if we look how many systems it takes to accumulate half of the total performance in the top 500, that number has gone down quite tremendously. And now we are down to 7. So the first 7, not even the top 10 anymore, the first 7 systems accumulate as much as the other 493 systems altogether. Okay? There is a tremendous concentration towards the top. We first noticed that in the research market, but I think it's becoming very evident that something similar is going on in the commercial markets. And the winners, they are obviously the big cloud providers, which are providing those big resources to commercial customers. So 7, that's a new record in terms of concentration at the top. My colleague, John Shelf, did a nice visualization, and so I borrowed it and redid it. We used to have that old rule of thumb based on Moore's law and based on how fast we grew the node count, that it took about 11 years to get a factor of 1,000 improvement in performance. And that is something which we even after the NAR scaling prevented us from, the end of the NAR scaling prevented us from further increasing cycle frequencies. We still managed by increasing our system sizes and holding on to our systems longer. To maintain that factor of 1,000 in 11 years, we managed to do that up till 2013. And then around 2013, as a community ran out of steam, we couldn't compensate for the lack of frequency scaling by increasing our system sizes anymore, because our systems had gone so big and it had started to consume so much power that we ran into other problems there. And at the bottom, we're running out of space at the bottom, which is the end of Moore's law. We started running out of ability to increase core counts on individual sockets. And those two features together, they started a tremendous slowdown since 2013. And now if you look at the very right end of the curve, if you look at how much performance increase you can expect just based on the hardware going out 11 years, you're starting to hit single digits. So it's a lot less than 1,000. We are below 10 at this point. So that changes the market and dynamic quite a bit. That changes buying behavior and that changes the importance of software. The traditional way to look at that, of course, is we draw the performance curves where you see the sum of all 500 systems in blue, which is basically 500 times the average. You see the number 1 system and you see the number 500 system. And we pointed out a long time ago we had these inflection points. First, we see them in the list first at the bottom, and then it takes some time. We have compensating mechanisms if technology scaling fails. That's why it took 5 years for the end of the NAR scalings to propagate from small system to large systems. That coping mechanism was accumulating larger and larger systems, building larger and larger systems. But at some point, that coping mechanism failed in those 2013, and since then, we can't grow systems anymore. Now, if you look into these data in more detail, we actually find a new inflection point in 2017. That one has shown only at the end of the list so far. That one, and I looked, and I have presented those data in the past. I looked around in all the technological variables which we collect about these systems. What was the correlate indicator for that? And the best correlate to that inflection point is the number of cores macroscopically in the system. So you see if you look at number of cores in the system, you see basically 3 phases. First phase, the first curve was, the first real curve was up to 2004, single core chips. And the increase in core count then is just increase in nodes on the macroscopic scale of the system. So we built larger and larger systems, but most of the performance increase actually came from frequency scaling under the hood. When frequency scaling stopped, we compensated by switching to many multi-core and many-core chips. That's 2004. So the core count started growing much faster. Okay? That was switching to many-core chips, as well as still increasing the overall system sizes. And around 2017, we ran out of steam. And I believe we ran out of steam at the bottom, that we can't increase the core count on the individual devices anymore as fast as we could before. And we're running out of steam at the macroscopic top end because we can't really increase our systems macroscopically anymore. We can't bolt together more nodes to compensate for the nodes not growing as fast as they have been before. So if you look at what happens in terms of performance growth since 2017, I just take the old curve and just show that rightmost part since 2017. And I do a very naive exponential extrapolation. And I see, even so, the blue curve is still too optimistic because it hasn't really seen that impact from that 2017 inflection point yet. Only the red curve has. Even with that, the blue curve doesn't quite reach 10 exascale at 2030. And the reality is probably going to be even worse than that. So we clearly in a very different environment than we used to be just 10 years ago in terms of what we can expect in performance growth from our systems, which then in turn makes software improvements and algorithmic improvements and math in terms of how we can accelerate time to solution much more important. Because at the end of the day, we really shouldn't look just at the floats we get out of the hardware. We should look at time to solution. And math and algorithms play a big role in terms of time to solution. But going forward, they are going to be even more of the weight of getting faster and faster solutions is going to be on the software side, not so much on the hardware side. Okay, so with that, I like to switch to the more traditional statistics about where systems are installed, who manufactures them, and things like that. And I'm going to show one pie chart about the whole list, and then I'm just going to focus on what happened the last year. So if you just look where are these 500 systems installed, you see now United States in a number of systems is ahead of China. That wasn't the case a couple of years ago, and behind that is obviously the political situation that Chinese manufacturers don't provide any insight anymore and Chinese customers neither in where systems are installed in China. China has become very opaque to us. We don't know what goes on in China. And the Chinese systems are just aging out of the list. So we don't know what goes on in China, but okay, that's what it is. You see the other countries is very much what do you expect, a mixture of Asian and European countries. Now, if I look at what happened the last year since SC22, I see on the left-hand side, you're always going to see a pie chart based on the number of systems. On the right-hand side, based on the performance of those systems have. So on the left-hand side, you see half of the systems, new systems on the list, were installed in North America, and that's mostly the US, followed by Europe and Asia. And Asia, that is China, and together with Japan, obviously. So if we look at the second pie chart where we do this by performance, you see the influence of the big systems. And the big systems here is the systems which were installed last year. So you're not going to see a Frontier, and you're not going to see the impact of Fugaku or something like that, or Lumi, because those systems are older than 1 year. You see the impact of Aurora, and you see the impact of Eagle. So that's why the blue chart is much larger than the red chart, because the number 2 and 3 systems, they're both in the US, and the number 8 and 9 system, the number 8 system, which is in Europe, is so much smaller that it doesn't bump up the red slice that much. It bumps it up compared to Asia, but not overly, not that much. So this is more what were used to 30 years ago, 20 years ago, before Chinese pushed into the market. Now it's a little bit driven by not knowing on what goes on in China. So where were these systems produced? Now that I always said we don't know anything about China, you're going to be surprised. Of course, there is a big Chinese slice. 38% of those 91 systems, 37 or what it is, were actually manufactured by a Chinese manufacturer. They are all coming from Lenovo. It's the only one. And all but one of those systems are installed outside of China. So we see the Chinese systems installed outside of China for a variety of reasons, but we don't see them inside of China. Those systems tend to be a little smaller. That's why the Chinese slice in terms of performance on the right-hand side is much smaller. There are research installations, in particular in Europe. There's a couple of research centers buying from Lenovo and using them as integrator. But there is a lot of commercial installations, and a lot of the commercial customers for Lenovo are actually in the US. So it's not just Europe. Other than that, mostly the other thing, if I break these slices now really down into the individual manufacturer, the one thing to notice is, or the things to notice is you see Lenovo is the Chinese slice. The US slice for the last 12 months, that's my disclaimer, that's really HP and Intel as integrators in terms of number of systems. And in Europe, it's Eviden, which is actually quite sizable, a nice success in terms of the market. If you look at the right-hand slide, you again see the influence of Aurora and Eagle in terms of the Intel and the Microsoft slices being much larger. And if you go around HP and Intel, much smaller. The ARM chip, the ARM slice, Fujitsu slice is much smaller. Fugaku is not in this installation, in this statistics. And Frontier is also not counted in the statistics. Okay, so what chip technologies did we see? It's a number of systems. Main CPU is roughly divided between Intel and AMD. Of course, if you count how much performance those contribute, again, you see the oversized influence of Aurora and Eagle. That's why the Intel slice this time is so large in terms of performance. But this is only the label on the sticker on the CPU. This doesn't tell you where the GPU comes from. That's this statistics. And in terms of GPUs, accelerators, clearly NVIDIA sells the bulk of it in terms of number of systems. If you sort it by performance, because of Aurora, the Intel Sapphire technology gets a big bump. That's why the red slice is much larger. So that was the exciting new installation technology last year. And if you combine those, I show both labels combined now between CPU and GPU. You see the commercial market, or not commercial market. If you just go by number of systems on the left-hand side, that the majority of systems is still installed without accelerators. So more than half of the systems either use an Intel or an AMD CPU and no GPU. Okay? And if you look into performance slice on the right-hand side, of course, you see if you really want to get performance, you have to have an accelerator. There's no way around it. And again, you see the different dominant technologies for the last year. You're missing the slices for systems like Frontier or the ARM chip, Fujitsu, and those. That's the disclaimer for these statistics. So in summary, Frontier is still the number one. It's the only exaflop system which has managed to give us a number, to measure it and to give us. Yeah. We had a fairly nice turnover in the top 10 and the top 50, signifying new technology and new systems coming into existence. So that's very nice to see. It's very diverse. And the one prominent example for a new chip generation entering is the Intel Sapphire technology on the CPU and especially on the GPU side. That trend that we use our systems longer and longer and holding on to them, that hasn't changed. If anything, it keeps going. There is a couple of technological reasons on the lower end as well as on the macroscopic higher end. And one of the effects of those coping mechanisms with the end of Moore's laws, end of the NAR scaling, one of those effects is that we have a very strong concentration of compute power at the very top. And we see that now also in the commercial market, not just in the research market. I think it was there actually all along, we just didn't have the visibility into the cloud market. Yeah. Moore's law is clearly, the old Moore's law is over, and if we do naive extrapolation, getting something like 10x scale at the end of the decade might be a stretch. We might not be going there if we do business as usual. We need a saving technology, and be that something on the hardware side, be that somewhere on the software side. My personal bet is it's going to be more on the software side, but I think there are plenty of people out there which try to prove me wrong. With that, thank you very much.
Thank you very much, Eric, for that very extensive look at the top 500. So we've come to the end of the formal presentations, and now I guess we'd like to open it up for questions and answers. So are there any questions?
Yes.
All right. Maybe you can identify yourself and ask your question.
I apologize for my first name. It's Vladimir, but last name is not Putin. So Vladimir Kozlov, Light Counting Market Research. So thank you for a very detailed presentation, but the impression that I get from your slides is that HPC hardware is reaching the limits. But at the same time, we're hearing about companies like Microsoft, Google, Meta planning AI clusters which are 10 times larger than what they have today. Are they facing the same type of limitations? There is a bit of a disconnect between their plans and the data you're showing. So can you explain that?
So first, I think HPC, by its nature being on the bleeding edge, has always hit limits, and it's a question how we have dealt with them. And as Jack said the other day, the last 30 years we hit many limits and we overcame them. ECL was a dying chip technology, and we switched to CMOS and so on and so forth. There's always growing pains, but for a long time we managed on the hardware level to stick to that factor of 1,000 in 11 years. And now that seems to be more of a problem. And the question just is, how is HPC going to deal with that? The community going to deal with that? Is it still going to be relying on hardware? Is it going to be more switching to software? And towards that notion that we don't capture all the market in all detail, that's certainly true. Our visibility into the cloud market, for instance, is very limited. And that's a little baffling because, as Eagle shows, those systems are very capable. They can be very capable. So it should be a big selling point to a cloud provider to give us a number and show hi, right? The one difference I would say, while the Google farms and all those the things, that not the integrated clouds, but the server farms, why then never showed up in the top 500 quite that well, is that we deliberately have a focus on very tightly integrated applications. So we insist on having one HPL run across the whole machine. And if you just have a server farm, you might not do very well on that. You might, and that's by design, because we are still believing that a lot of research is done with very large applications, doing very large problems. That's a focus we keep. And that's why we never, for instance, allowed throughput measures. We don't track any throughput measure. By throughput measures, there would have been very large systems for a long time, but we are not that interested into that because that is not traditional HPC. That's not the corner where we basically specialize in.
So I guess the thing to add to what Eric has said is that, you know, the lens we're looking through is the HPL benchmark. So all the data that we have is looking at the industry through that. And if we had a different benchmark, maybe it'd be reflected in a different way. The other thing is, you know, we have had these transitions from scalar to vector to multi-core, from multi-core to cluster-based systems to GPU multi-core kind of systems, and we get a boost every time we hit one of these technology changes. And you know, I don't know what's coming next, but I hope it'll provide us with another boost. The other thing to recognize is it's not just the hardware. There's also improvements that are made in the software and also in the algorithms that can help boost the performance. You know, one of the things I'm interested in, a lot of people are interested in, is trying to use mixed precision to help boost, again, the performance, trying to leverage the idea that we can use shorter precision in parts of the computation, or use shorter precision plus some mathematics to help boost the accuracy of the solution while doing less operations. And there's always hope, I think, for improvements in bandwidth. So bandwidth is the killer in many of the things that we see. And if we could have better bandwidth and research into ideas that would lead to that, I think it would help the technology along.
Thank you. So it seems like there's still hope for improvements in hardware and finding new solutions. So
I'm always optimistic in terms of how we can do business. Yeah.
Good, good. Thank you.
Thanks for the presentation. Joseph Schulchat with UT. I was wondering if you had an intuition about how much the decline in the submissions from China adds to the shallowing of the curve. Right? So if you were to remove the Chinese systems from the historical data, will we see much more shallow development in the past already, right? So the shock that we're seeing now would have started much earlier. Is that, have you looked at that?
So we haven't done an analysis of that. I think that's an interesting point, and I think it's a valid point to make. We know of 2, maybe 3 exascale computers that exist in China that are not reflected on the list, and that would certainly bump everything up in terms of the performance and how we're looking at things through the HPL lens. So I think it is valid that there are machines which are not reported, there are machines outside of China which are not reported that would help give perhaps a better vision of where things are going or the trends that we see. But because of the lack of submissions in China for geopolitical reasons, machines in the US because of perhaps security reasons, we don't get a very clear picture of how things are.
Right, so what I was getting at is maybe we have had an artificial bump. So, I mean, the top 500 has spent the time when China was not submitting data, right? So if we just look at the countries that have traditionally.
So the way, and probably the reason that I use it as an excuse that I never did that analysis is I look at it with 2 different angles, which I usually do, which is looking at number of systems. Sorry for that. Number of systems, and I look at the installed performance. So what the Chinese did when they started submitting systems to the list, there was an influx of a large number of small systems. So if you look at the statistics based on number of systems, those had a bump and those would change for a couple of years, and those systems are aging out now. But if you look at the performance, at the statistics in terms of performance, installed performance, those, even if it's 200 systems, if they're at the end of the list, they have a very little influence in terms of performance because the list is so top heavy. So with respect to performance, those 1 or 2 systems in China, which we officially don't know about, they submit papers about it, running on it to Gordon Bell, get Gordon Bell prizes, but they don't say what the Olympic performance is. Yeah. Those systems would have had an influence the last couple of years, the last 2 years or 3 years, on the performance side. But if you're interested in their impact, there is only 1 or 2 systems. You can easily download the Excel spreadsheet and fetch it with an imaginary Chinese system and see how much that would actually change this.
Okay. If I may, a second question, I don't know if someone else wants to ask. There's been a lot of talk about hardware specialization here and in last years. How do you see the role of HPL in that when we might have hardware that does not accurately, that focuses on a different kind of compute than what HPL does? And do you think that our focus on the top 500 might actually impede those developments?
Well, as we're in this climate that we don't have easy hardware improvements anymore, architecture becomes more, the differentiation between different products in the market by architecture becomes more and more important. And we see that in the big number of startups trying to build hardware for new specialized cases, the most dominant one obviously being AI and machine learning, right? So the way I look at that is I thought, what do we need to do to track those guys? Of course, you can try to do an AI benchmark, and there is both sessions about that tomorrow on lunchtime, I believe. But then I thought, okay, we are more traditional engineering, scientific calculations, and HPL is signified by that. And HPL mixed precision benchmark is a benchmark which should run well on an architecture which is geared towards AI because it's geared towards mixed precision, right? And if it can't run HPL MXP, then I would like to understand why. But I think that would be basically my approach to trying to include other types of architectures. Of course, there's limits to that. Yeah. If you think about quantum processes, I think Jack started an HPLQ project, but I'm not sure how far we are. At least I told him he should, but I think we are not going to go very far with that, right? So there is a limit to what HPL can do.
I did not do that. That's did not do that. That's right.
Thank you.
So I have to say that I'm just happy that with all the new hardware coming in for machine learning, I'm just happy that we still have 64 bits precision in many of our processors.
Hi, Saurabh Chakraborty from Samsung. So if we look at the MLPerf benchmarks, they try to capture time to solution for a variety of problems from a few different domains. But in HPC, so we generally look at HPCG and HPL as the two extremes. So do you think they are sufficient to capture the improvements in hardware, software, and algorithms in an effective manner, or should we also think about having a wider variety of benchmarks that kind of falls in the middle?
Well, to me, it's obvious that we need a whole suite of benchmarks that probe the system at different points that we can use to help understand the benefits of a given architecture. And having one or two is not the way to do it. It's to have a whole suite of things that we can use. And then we should be able to dial up how our application runs based on that whole suite, plugging in the right numbers and coming up with a metric for a given machine. So I just think we need more and to have it done in a systematic way. So I'm looking forward to seeing the outcome from Jack Wells's BOF tomorrow afternoon, where different ideas will be pursued, I hope.
Thank you.
Howdy, I'm Corwin Lester from Oak Ridge National Lab. Given the trend of commercial systems gradually placing higher and higher and higher on the top 500 and the incentive for large language models and AI becoming so commercialized, do you guys imagine a future, a recent future or near future, that commercial system even places within the top system or top 4 systems?
I have no doubt that they could easily be number one today. It's just a question of having them put the resources into developing and running an application. So there are centers, cloud centers, which have the ability to place number one today.
Well, if you just look at the amount of money involved, you realize that the big companies spend as much money as the big centers can spend. But the one thing the one caveat there is, of course, if you look at something like ECP, there is a lot of money which goes into software environment, the whole ecosystem and applications, right? So that there is much more to actually having an HPC center than just buying big iron, right? Mm-hmm. And of course, the big cloud provider, I mean, they have to do that too. They have to have their own ecosystem and build into that. And if it really becomes competition between big cloud systems, then the software environment is going to be very important aspect of that.
Thank you.
No other questions? You're letting us off easy here. Did we give him back 15 minutes? Or is that it? Okay, well, thank you very much for attending the
I
BOF.
think there was one more.
Oh, one more, I'm sorry, go ahead, yes, sorry. It's hard to see up here.
Well, just to brighten up the conversation.
It's Vladimir again.
Yeah, Vladimir Kozlov, light counting. Any new technologies that you see on horizon? And I know quantum computing gets a lot of hype. Anything new that you can envision that could change the picture drastically?
Yeah, I'm not going to talk about quantum.
No quantum talk here. I think the one thing I'm following somewhat is the whole chiplet evolution, but that's been going on for a while already. And Rick pointed out, what was it, 47 chiplets, 47 for the data CPU for the Sapphire GPU. So that is one hatch, one escape hatch. I think the industry is trying to pull. If it's sufficient to really prolong growth curves for a long time, we have to see. But that's one of the developments, which is really, as we're running out of space at the bottom, we just need to integrate the chips we have. We need to either make them larger, like Cerebus, or we need to integrate the chiplets more tightly to squeeze more transistors in the same volume, right? And that within a power volume which is manageable. It's not an easy problem, but I think that's the way out. Because at the large end, at the high end, macroscopically, I'm not sure if you're going to be able to squeeze more nodes in the same machine rooms. And a lot of centers just built new machine rooms 10 years ago. So.
Okay, I guess we're done. Thank you again for attending. Look forward to seeing you at the ISC meeting in the end of May and middle of May, and back here next year in Atlanta. So thank you so much.
Thank you.